For this. So welcome to the Friday afternoon session of the 2023 Dev Conference. And we've got Reese Mainwaring giving a Gazebo update. And unfortunately, Reese wasn't able to attend in person, but we hope that this will work well as a remote presentation. So over to you, Reese.
Thanks, Tridge. So this is an update on the Gazebo simulation, and there've been quite a few changes to Gazebo over the past couple of years, and so we've managed to incorporate most of those changes into our integration with ArduPilot through CIDL. And this is a run through what we've done to make ArduPilot work with the latest version of Gazebo, and then a walk through some examples. So the outline for the talk is kind of a review of what's new, then the changes that we've made to the plugin and some enhancements there to add some extra features to take advantage of some of the new things in Gazebo. A couple of tools that are kind of not integrated necessarily with the ArduPilot stack, but that I find quite useful for working with the new tools from Gazebo, and then some next steps. And then on the second part, a review of some of the models that we've made available and ported over to the new version. And then a case study, which is a sailboat simulation, which is really where I got started with the ArduPilot work a couple of years ago, when Pete Hall asked if we could take some of the work I'd been doing on wave simulation and apply it to the work he'd done on sailboats originally. So we'll have a look at that towards the end. So Gazebo has undergone quite a big change from its first version, which was used with ROS 1, to its current incarnation. It's gone through a few name changes, but they're back to Gazebo now. And it's shifted from being a fairly monolithic application into a customizable toolbox of simulation libraries and other features. And pretty much everything around the environment is customizable now. So it's written as a series of about 9 or 10 different core libraries. And each of those is arranged as, well, most of them arranged as sort of pluggable. So the simulation physics backends, the rendering engines, the sensor plugins, each of those can be swapped out for a different backend, and the Gazebo team provide defaults for all of them. But if you want to, you can replace the entire physics backend with another sort of 3D physics system. So it's using Dart now as a backend, which is fairly solid physics, sort of rigid body engine. The big change on the rendering, it's improved quite significantly over the earlier version. So Ogre is the render engine that they use. There's a new version of that which supports physically based rendering. So the lighting and shading is quite fancy now. And some of the demos which I've put up there on the screen are from shots that the Gazebo team have put out with various releases that they've done. The sensor system is quite a lot more advanced than it was before. It's much easier to add custom sensors. It used to be quite difficult. They've got a fairly rich camera system that comes along with the improved rendering engine. So there's things like, there's the standard RGB cameras, but also depth cameras, thermal cameras, stereo cameras, as well as things like segmentation cameras for chopping up pictures into boxes for AI analysis. The simulation engine has been really reworked, and it's more designed now like a game engine. They use this entity component system, which is quite abstract, but it allows you to extend the system with plugins probably a lot easier than before. So all the features, all the simulatable features are attached as components to entities within the system. So everything that you might think of as an object within the simulation is just an entity. It's given an identifier, and then its behaviors are modified by attaching features to it. So something that is a link or a model in the library, you attach things that might be interesting physically to it, like it'll have a pose, it might have a velocity, it has the ability to be subjected to forces and things like that. So depending on how you want an entity behave, you just attach components to them at runtime. And that makes it very, very flexible to work with. And so the system can be as lightweight as you like, or you can add quite a lot of complexity to an individual entity within the system. The GUI itself, it's Qt based. And again, you can add Qt widgets as plugins. So if you've got, and we'll look at that a little bit later. It has a bridge to ROS and ROS2. So this is it's called ROS GZ. I won't go into that too much, but I think that's going to become probably increasingly interesting with some of the work that has been done with the ROS integration into ArduPilot. So we'd probably be looking at using Gazebo as a simulator for that, and the bridge from ROS2 into Gazebo will be handy for that. So on the plugins, quick overview of what we're looking at. There's the kind of migration from Gazebo Classic, as they call it now, to Gazebo Garden, which is the current released version. We provided we swapped out the old interface for a JSON interface. There'd be some changes into the types of commands that you can configure in the controllers. And then there's some extra features where we've kind of added things like parachutes and gimbals and some extra sensors. So we'll cover those. The original port from Gazebo Classic to Garden, it was done by one of the Open Source Robotics Foundation's people, Brian Gerke, who did that for a version Gazebo 3. And this was a migration of Pierre's original ArduPilot Gazebo plugin to work with Ignition, as it was named at the time. And it's just a summary of the kind of major changes. So Gazebo Classic is called using sort of Gazebo, and the object that you want to launch as a world file. It's a XML file using the SDF format. And there's a new set of command line tools in Gazebo Garden. They're all prefixed with GZ, and then there's additional verbs. So sim launches the simulation, but there's also topics and services that you can call using the same command line set. And everything is just called a .sdf file now. The plugin, so the original plugin, there's links here to Pierre's original plugin, and we still kind of got maintenance support of that. And the new plugin, we've kind of moved under the ArduPilot org, and you can see the link there. There's changes in the way that the plugins are constructed. So in the previous version of Gazebo, you'd have plugin specific types of plugin according to whether you're working with a model or changing a GUI or something like that. In the new version, there's just a series of abstract interfaces which you attach to a general concept of a system plugin, and you implement the things that you want it to do. So the update system has changed a bit. There used to be just a single update, and now there's a 3-phase update step. So there's a pre-update where you would apply all the forces in your custom plugins. The main update step is where the physics engine itself time steps the equations of motion. And then there's a post-update step where you would query the results of the time stepping for sensor information and other things you might want to feed back into downstream state. So for example, the ArduPilot plugin acquires all the information about the pose, current accelerations and velocities, and ships them back to SITL. And it's a fairly abstract system to work with to start, but it's very powerful in that everything is a system. So once you have written a couple of plugins, it becomes quite clear that it's a much easier system to work with. The changes so there's quite a big change in the plugin, and that's all been migrated across now. In terms of running existing models and worlds that you may have, the big change, I think, is probably in the materials. So any previous models that use the Ogre scripts are not going to work in the new environment. So you may need to modify existing models to use either very simple materials or proper physically based rendering sort of sets of data where you provide things like the normal maps and the diffusion maps and bump maps and things like that to fully specify the way the thing's going to appear. And because everything's a plugin, it's a little bit more effort up front to configure the world. So previously, most of the systems that you'd want to have active when you ran the simulation would be available automatically. In the new setup, you have to enable them all with plugins. But once you've got an example set up, it's fairly easy to follow. We've used the JSON interface. We've retained the Sim Gazebo for the legacy version. The main differences are in that they both sort of receive a binary servo packet, but SimJSON has a versioned binary servo packet, and that's quite useful because we've been able to use that feature to upgrade the support to have 32 servos as well, and we'll discuss that a little bit later. The data that gets returned is now just a JSON package, as previously it was a binary state. So that means that it can be, a lot of the fields can be optional. So some of the sensor state that gets returned is optional, and if it's in the package, then SITL picks it up and starts passing it on to the appropriate backends. One of the main changes, and this is probably a theme that'll be going through in the way that you control, you translate the servo pulse width modulation data that comes from ArduPilot into commands that get used to control joints or various other bits and pieces within the simulation. So originally, ArduPilot would have its own controllers, the plugin for velocity or position control, and when you set up the model, you would specify whether you want a joint to be velocity or position controlled. So rotors, for example, would be velocity controlled, and then you'd have to assign the PID gains for those. But as we had a request from Clyde McQueen, who wanted to get his blue ROV simulation running using the new version of Gazebo. And so what we did is we forwarded the command straight through onto the Gazebo message bus. So there's a GZ topic layer. And so the changes are, rather than try and apply the commands within our plugin, we just forward the command on. We may normalize it slightly and offset it, given kind of information about the offsets and multipliers. And then we specify a topic that we want this command to be directed to. That goes on to the ignition bus, and then it gets picked up by the appropriate plugin. In this case, we're targeting the thrusters plugin, which is something that a plugin that is provided as part of the Gazebo package. And so we configured the ROV to use the standard thrusters with Gazebo and just redirected all the servo packages through to that. So I think increasingly that's the way we're probably going to be using the plugin, is rather than actually controlling joints and positions specifically, we'll just forward the commands on to the appropriate plugins within the Gazebo packages. It's quite a nice example, this one, because it also uses it uses the ROS bridge, and it's got a MAV-ROS2 connection. So if you're looking for an example of how to use Gazebo, MAV-ROS, and ROS2 with ArduPilot, then I'd recommend taking a look at Clyde's Blue ROV ignition example. So some other things we've added. There used to be a parachute. I don't know if there was previously a parachute plugin, but there is one now. So Alex Molchanov asked if we could get that working, and we worked with him to provide that. So that uses this feature where you can have detachable joints. And again, we're using the command technique. In this case, what we're doing is just triggering a release command. So when the servo goes high, the command release goes high, and there's a custom plugin in this case. And what happens there is that you specify the link you want to attach the parachute to. There's a model, which is the parachute, and then there's a pose, so how you'd like that parachute to originally appear relative to the model when it gets deployed. And then there's the target topic that it's going to receive. And when that plugin receives a topic, it triggers the parachute, and off it goes. So this is configured using the standard setup within ArduPilot, so it's parameter setup, and it works very nicely. So that's a new feature we've added to it. Okay, whoops, run ahead there. Another thing we've modified is that there's original versions of the plugin had facility for a camera and a gimbal to be attached to the Iris quadcopter. I upgraded that, so I gave it another degree of freedom. So the gimbal now is a little 2D gimbal with a camera attached. And previously there was a custom plugin within the ArduPilot package for dealing with the controller. But now we can just use one of the standard, well, actually two of the standard joint position controllers that are available. And again, we just forward the commands onto those, and the plugin delivered was part of the Gazebo packages are quite sufficient for moving those around. One of the nice things about doing that is that you can test it by sending the commands to the topics directly. So before you've got the CIDL up and running, you can launch Gazebo, you can send topics to the commands to the topics to control in this case, the roll and tilt joints on the gimbal, and check everything's working properly. So by breaking the system up into having the plugin receive the servos from the sort of SimJSON backend, and then forward them back onto the transport layer, it makes testing the various parts of the model and the simulation a little bit easier, because you can break it up into testing the Gazebo joints, respond to all the commands you expect, and then you've got the mapping of the sort of commands coming from ArduPilot into the expected sort of ranges that you would like to have. Okay, so the nice thing about the JSON API is that it's extensible, and I haven't extended any of the fields that were there. So I've just used the ones that were provided but weren't populated. So we've added a facility for range sensors. So the JSON backend supports up to 6 range sensors. Now, there's many things that have been ported over from the classic version of Gazebo to the new version. The sonar sensors, unfortunately, are not included in that. However, we can proxy them using the GPU LiDAR sensor, and just limiting the scan beam width and range, and then attaching a number of those at various points on the model. You can feed those through into the JSON package that's returned back to CIDL. And the configuration in ArduPilot is as standard and documented in the wiki. So we just set up the rangefinders from 1 to 6, specifying their poses relative to the frame, the body frame. And there's an additional set of fields that gets attached into the ArduPilot plugin XML package that just state the type of sensor, an index for which particular range slot you're going to target, and then again a topic, because the sensors will listen to information, the plugin will listen to information published by the sensors on the topic. So when you set a sensor up, you can specify what topic it's going to publish to, and the rate at which you want that sensor to publish. So sonar sensors in this case are being published at about 30 Hertz. So that all works quite nicely, and you can see it all plumb through into MAV proxy. So as the rover spins around, we can see the distance sensors hitting the wall and measuring them, as you would hope. Another type of sensor, in this case we needed it for sailboats, is a wind vane or anemometer. So again, there's a slot available for that in JSON that we weren't using before. So in this case, it's not a sensor that's available in Gazebo. So we've written a custom sensor, and there's two parts to writing that. So you write a plugin that is the sensor itself, and then you write a system that basically monitors all of the anemometer sensors that you've added, and aggregates all of those results and makes those topics available for other systems to use. And the way we've tested that is that we've added the plugin to just a block, and set up the wind to be coming, in this case it's coming down the -y direction. And then as we spin the block around, we're using the Sail plugin in MAV proxy, and we've configured the wind vane in parameters in ArduPilot to pick up the true and apparent wind. And as we spin the block around, we can see the data all flowing through nicely. So that's all working quite well. And we've got another set of sensors. And then the most recent thing we've changed is, so Buzz suggested we try attaching a whole set of rotors to a hexapod. And as it turns out, that's quite a straightforward thing to do in Gazebo. So it doesn't have the best aerodynamics, and we'll talk about that later, but it does have the ability to handle lots of quite complicated joints and structures. So it's an ideal simulation environment for prototyping this type of thing. But it's got a lot of servos. So the previous API supported up to 16 servos. To extend it, we added another servo packet into SimJSON. There was a few other minor changes to make in order to be able to have the servo 32 enable parameter made available. And then what on the ArduPilot side, what happens is that if the servo 32 enable is set, then SimJSON sends out the 32 channel packet, and if it's not, it sends out the 16 packet channel. So and the failback is to the previous behavior. They've got different magic numbers on them. So on the plugin side, we just needed to add an extra field to say if you have the 32 channels or not, and then you check to see whether you've got the right magic number on the servo packet as it comes through. So that's quite nice. Meant then we can have, in this case, we've got 6 rotors and then 16 leg actuators. There should really be 18, but at the moment you can target up to 16 scripting channels. So in this particular case, there's a Lewis script handling the mixing and unfolding the legs. It's using the dynamic scripting matrix because at a later stage, we want to have a look at being able to alter the configuration of this thing while it's in flight. So at that point, the mixer will need to change at the same time. In this case, it's just replicating the hexacopter. And the 16 scripting channels are used to drive the leg servos. So that's a kind of nice example of doing that. But all of these things I think have now been folded into the master branch. Okay. Right. So there's a few tools. Now these are not as part of the ArduPilot package, but we may kind of get them upstreamed or incorporated either into Gazebo or somewhere else. So the first one is force visualization. So with all of these plugins, you can modify the simulation to add plugins that apply different types of forces. So in this case, we're looking at a set of different types of sails. We've got wing sails with elevators, or soft sails, and we're writing a custom set of lift and drag plugins to deal with the forces that we'd expect these to experience in the presence of wind. But there are many other plugins active at the same time, and so if you want to try and attribute the particular set of forces arising from a plugin to the resultant behavior of the system, it's quite useful to be able to switch the forces on and see them, and it was quite useful for doing this. So this is a visualization plugin. It's an example of how you can extend the GUI to subscribe to information that has been sent around the simulation, and add extra visualization as well. This was used to verify that the lift and drag were correctly aligned with the incident wind and the appropriate sort of link frames of the sails. The way it works is that the GUI plugin itself has access to the entity component system. It gets an update. You can query that for information, including forces that you may have published from other systems. Another tool, and this is something I wrote. I wrote a set of Python bindings for two of the libraries. So GZ Transport uses 0MQ for shifting all the data around, and the messages it sends are Google protobufers, and there's two libraries to handle this. And the Gazebo sim doesn't provide bindings for these in Python, but actually, if you have access to the messages, you can control most of the simulation. So rather than write a series of bindings against all the objects and simulation objects and things like that, you can do a great deal by just having accesses to the messages and access to the transport layer directly. So here's an example where all the controllers, and mentioned earlier that these position controllers have PID gains, having to tune those, and you generally do need to tune each one within a simulation. It's very time consuming if you have to go back and edit the XML, restart your simulation, and relaunch it every time. So you can write a service on the joint itself, which will subscribe to, which will respond to an input message. And in this case, not shown here, but complementary to this is the controller has a service which allows you to set the PID gains. And then you can write Python scripts to target it directly. And what's quite nice about the fact that the protobuffers is that you've got a native mapping through from the sort of natural bindings provided by the Google protobuffer libraries into GZ's transport using two binding libraries, and these are pybind11 and pybind11 protobuf. And it all just works. So you can declare all your messages in Python. You create an instance of the transport layer in Python, and you just construct the objects. The callbacks, so they are you've got like the C++ transport layer calling the Python callbacks and returning the messages. So it works as you would want it to work, and all the binding and marshalling just happens under the hood. So that's quite nice, and hopefully we can get this upstreamed into Gazebo. So sort of talking to the team that are looking after the GZ transport layer at the moment, and they seem quite open to adopting this approach. They're going to change it around as suits them, but I think that the principle of having a Python binding layer to the message and transport layer is something that is quite useful. Where it's handy is there is a bridge. So the ROS GZ bridge does do a similar thing. It's a series of C++ libraries. However, if you wish to get a new type of data shipped into ROS, you need to modify that library and provide the mappings for that. And there are many things. The set of things that you might be interested querying the simulation directly is much larger than the set of standard messages that you'd put through onto a ROS bus. So if you just want to quickly go in and plot some data or control the simulation or modify it somehow, having a direct Python binding to the simulation layer is very, very useful. So there's a library for that, and I mean, I've certainly found it quite useful in putting together simulations and testing. Okay, so there's a bit of a intermediate next steps here before moving on to some models examples. So this is a quite extensive wish list of things that would be nice to have and lay out a potential program forward. So there are quite a few sensors available now in the standard Gazebo simulation package: altimeters, air pressure, airspeed, batteries, many cameras, magnetometers, and navsat. So the question is like, what's the best approach to integrate these additional sensors into the simulation? So we can get the data out of Gazebo, we can map it into whatever form we like. I don't think all of this data should be going back through the JSON payload, but the question is, what's the best way? So that's really something I need to follow up with the dev team, and I think there's maybe some of the work with the ROS2 layer, it could go through that, or there may be other methods of mapping it through. But I'm not sure how to best approach this, but there's additional information it would be nice to be able to pull back from the simulation and forward on into SITL. On the environment side, this is probably more on the Gazebo side than the ArduPilot side. So these sensors need to have sensible environments in which to monitor, and they're fairly simple at the moment. So you've got these various vector or scalar fields that you can specify, and I think there's room for improvement on the Gazebo side in order to set these up. There's some open questions. So the component system doesn't currently specify an order in which the updates occur. So everything that's a system that has a pre-update method gets lumped into one schedule. And you can't really control at the moment whether you update things like the wind and the waves before you update all the things that need to measure them and then apply them in the physics step. So you're not really guaranteed that the environment will be updated prior to the physics system that's using it. So I think there's some scope for improvement there. Things like the wind effects and system updates, they do a couple of things. They update the field, and they also apply the results of those fields to the various links. And I think they should probably be separate. So you have a set of systems that updates the environment, and then you have a set of systems that queries that and applies it. Where they are coupled, it's quite hard to get into the information that you need. So they could change. So there's some things that could be improved there, and then you could have different ways of you could have quite complex systems for modifying the environments and the sensor sets to feed them back into into the controllers. On the physics side, so Gazebo is not a great aerodynamics simulator. It has a model for lift and drag. It's very simple. It has piecewise linear lift and drag coefficient curves, which you can get to sort of work, but I think there are lots of effects that are not really accurately modeled. So there's a question of like how can you improve them? There's 3 different methods of providing thrust for quadcopters. There's 2 main ones. You can either control a joint velocity and then apply lift and drag to the rotors, or there's a dedicated model for doing that. Now they have slightly different interfaces, and so they're a little bit different to get to. It would be nice to homogenize those, and I think there's some work to do that. And there's other tooling around the kind of these models which would make them easier to use. So being able to replicate thrust and torque curves, or just specify those and have the models created to match them would be very useful. There's some discussion in a PX4 discussion group about suggestions of perhaps the multi-copter model could be reparameterized to make it easier to set up. I've noticed that in the approach that we've generally used in ArduPilot of joint velocity with the lift drag plugins, there's some stability issues using that for particular models where the Swan K1, it just about works with it. I mean, it does work, but it's not great. The Omnicopter, I cannot get to work with the driving lift and drag, driving rotor lift and drag by spinning a prop and then calculating the aerodynamic forces on it directly. So there's something funny going on there. So generally improving that would, improve the behavior and accuracy of the aircraft. For rovers and boats, as we'll come on to, I think the modeling is getting pretty good. So it's not specifically a aerodynamics environment, but in a very speculative thing, if that was something that people wanted to do, then you do have the facility to replace the entire physics system as a plugin. So, with a great deal of work, you could replace the plugin library with an aerodynamics library such as JSB Sim. You could have the proper Earth-centered inertial coordinates. You could do all of that. It's very far from clear whether that's an undertaking that's worth taking on. Something else that would be quite useful is being able to abstract the joint position and velocity controllers behind servo and speed controller components. That wrapped up all the PID tuning, made it easier to configure to a physical spec, and added battery usage and that type of thing. So, so really you have a model, you attach kind of servos and speed controllers to it as you would expect, and you just then plumb the pulse width modulation kind of commands forwarded from ArduPilot straight through into those, and you try and make it easy to set up. At the moment, it's quite time consuming to set up each of these controllers properly, because different vehicles, they have different inertials, they require different PID controllers for each of the joint or velocity controllers. So making that easier would make it an easier process to set up new models and get them running properly. There we are. Okay, so that's really the work that's been done on the plugins and the system side, and then we also have a number of example models as well to use with all of this. So in addition to the Iris quadcopter and Zephyr that was provided with the original plugin, we've put a bunch of stuff into CITL models to use different features and provide platforms as starter models for people who might want to use the simulation for testing things. So example, we can have custom rover frames. So this is example of Roger Chen's Sorpy rover. So it's a Curiosity style rover. It's got 10 joints, it's got 6 wheels, four of them are steerable. It's quite nice because it can do in-place steering, which makes it amenable for the ROS2 SLAM nav2 packages. It's a Lewis scripted motor mixer, so it uses some of the nice new features available with an ArduPilot for scripting, and applies them to models which are quite nicely specified in Gazebo. Another example is for marine simulation, and a bit more on that later. This is just like a simple buoybot type model, PVC tubes with a couple of thrusters on them. So it's essentially a skid steer rover. There's quite a lot of physics going on. So there's the wave modeling for the environment. There's a set of hydrodynamics being applied to each of the hulls. And we're set up with, like, in this case, there's a sensor package on it, includes the inertial measurement unit, which is essential for getting the ArduPilot integration, but we've also got a magnetometer, camera, and a navsat attached to it as well. So these are all working quite nicely, and we can add these packages into suitable models as we go. And then things that are already available, a selection of quad planes. One of the quadrupeds that was done as a GSOC project. We kind of took that and put the model into Gazebo. There's some environments and some rovers and some experimental craft as well. So it's pretty flexible in what you can put together. I think targeting rovers or multi-vehicle type simulations, or things that are a little bit odd and don't kind of fit somewhere else, Gazebo is quite flexible for taking those on. Okay, and then the last thing is, this is kind of back to putting all of these pieces in place to properly port the original Sailboat model over, so that it works correctly in Gazebo now with all the new features. So this model is based off a Racing Sparrow 750. So the designer, Brian Hever, was very kind, gave me permission to use his CAD model and make that available. So I've scaled it up slightly in the model. It's supposed to be 750 millimeters. It's actually double that size in the simulation. But it's quite a nice model to work with. So the approach for this is that the first thing you need to do is to make all the visuals and collisions available. So Blender's the tool for that. So the visuals in Gazebo are like either STL or Collada files, and so Gazebo is a good tool for exporting those. The collision mesh for the marine simulations needs to be cleaned up, because the physics is applied to the mesh directly. So each triangle has it's determined whether it's currently below the waterline or on the waterline. Triangles get cut if they're on the waterline, and then the hydrodynamics forces get applied to each triangle. So the mesh needs to be clean. You need to have as fewer triangles as possible to make it run real time, but not so few that you lose the essentials of the shape. So there's a bit of work there to tidy it up, and that's part of the preparing the model. The physics system itself, there's three main things going on. There's hydrodynamics, so that has a hydrostatic buoyancy. There's a couple of drag forces that are applied. There's a viscous drag, and there's a sort of pressure type drag that are applied normally to each element. You can see in the diagram, the green area is the current submersed area. So that's where the forces are applied. That's changing as the waves are changing and the boat's moving. So all of that's getting recalculated. And then we've got two lift systems, one for the foils, for the fin and the rudder, and then a lift system for the sails. As mentioned before, we added an wind vane anemometer goes through. So the green circle in the dial is a top-down view. We've got like a sensor on the top of the mast. There's there's transforms to put that into the side of the kind of the FRD body frame that that ArduPilot's expecting. And then we've just got some checks using the Sail module in MabProxy to make sure that the apparent and true wind is coming from the directions that we expect it to. The sails themselves, they need a custom controller because you want the sail to be able to, if you haven't sheeted it in tightly, you want it to lie to the wind. So it's a type of joint position controller, but in this case, you only apply the force when the actual angle is the absolute value of the angle you want is less than the actual angle. So you pull the thing into its target position, but you don't kind of apply any force if it overshoots. So that naturally lets the sail just, if it's not sheeted, it'll lie to the wind. And as you sheet it, it kind of comes into the center line, but it also means that when the boat tacks, the sail comes across correctly. And you don't have to control that. And then finally, there's the plugin itself. So we've used this command forwarding technique. So there's commands are forwarded onto the rudder and sails, and autonomous sailing is set with the sail enable flag and the parameter set, and it all comes together. So yeah, and then that's kind of the speed run through it. So there's a video to play, and if there's any questions, it may be a bit hard for me to hear because I'm remote, but yeah.
All right, can you hear me there, Reese?
I can, yes.
Great. Okay. I think I will need to relay questions from the audience.
Yes.
It might be hard to get the microphone to go through to you otherwise. So questions from the audience? Yes, Rishabh.
Do you think I should just unmute?
Yes, you can unmute there. Yes, indeed. And I'll mute here.
Hey, Reese, can you hear me?
Yes. Oh, not now, sorry.
Wait.
Reese, you need to mute while Rishabh unmutes to ask questions. Okay, great. Rishabh, you can unmute.
Reese, can you hear me?
All right. So what's the question, Rishabh?
So I wanted to ask him about the camera APIs, like how do you access the camera on, say, a Python script? And I also wanted to ask him, okay, just first question. Yeah.
Okay, so he wants to ask about the relaying of cameras via Gazebo. So can we get input from camera systems? I'm guessing computer vision type applications. So if you wanted to do visual odometry or avoidance applications, how would you pipe through the video data to be able to process those with a Python script at some point?
Right. Yeah. So there's two approaches, I think. So you can, so that the ROS GZ layer has a mapping of the camera sensors through into the standard ROS image messages. So you could use that, or you could do it directly with the Python bridge layer that I've provided, or you could write a C++ plugin to do that. So there's a number of ways that you can get access to the messages. I think if you had tools that already processed them from the standard ROS image messages, then the bridge is probably the way to go. But that puts a dependency on ROS2 for your system. So it really depends on whether you want to do that or not.
is because they have firstly a really neat API to access it nicely and easily, but also that the camera is you can modify the parameters so they kind of really closely match your existing camera that you might be using on a hardware.
Right.
Is that possible on the simulator?
So Rishabh's saying that is his experience with AirSim, he could modify the camera characteristics, presumably the extrinsics of the camera, to match a real camera that he's working with. Is it possible to modify camera properties to match a real camera?
They are configurable. I mean, you would need to have a look at the camera sensors that Gazebo provides and see whether they have enough fields for you to manage. And so if the custom camera, if the current range of cameras, they do have things you can control the field of view, you can control the kind of various properties of the camera. It's sort of field of view, aspect ratio, pixel count, and things like that. I think if it didn't provide exactly what you wanted, then you'd have the option of writing a custom plugin to modify, to provide your own camera sensor, or modify one of the existing ones as you require. So the whole system is configurable, and I think that's kind of one of the powerful things about Gazebo, is that they've moved everything as a plugin. So if you don't have exactly the sensor that you require, then it's an option to write it yourself. And they've made integrating sensors into this sort of custom sensors into the simulation much easier. It used to be quite difficult to do that. It's much easier to add a custom sensor now than it was before.
Last question, also from Rishabh.
Yeah. So how easy is it? So for example, if I want to place an April tag, or a moving human, or just whatever, it's like a custom object inside the environment. Is it like really tough to do?
All right. So asking about adding custom objects inside the environment, such as an April tag. If you want to place that in the environment so that your camera can see it, you can do vision applications with that April tag. How easy it is to do something like that?
Yeah, I think so. I mean, there are many examples. I mean, that part of Gazebo hasn't fundamentally changed from the earlier versions. I mean, what's happened on the objects is that the ability to render them has got better, but the whole ability to place objects and models within the environment is much the same. So I think there are probably many examples of tagged objects. So if you did a search for April tags in Gazebo, and I think Shiv used that in one of the docking examples. So I think most of that transfers through. There are quite rich environments that have been provided examples. I think on the opening page, there was an example with the sub-T challenge where they created a cave system as one of the DARPA challenges, which has many objects, quite a complicated map. So I think that's possible. Doing that efficiently, I think, requires a bit of scripting rather than constructing the worlds by hand, but I think it's possible to do that, yeah.
Okay, well, I think that's all we have time for. That was absolutely fantastic, Rhys. Thank you so much. And really appreciate you joining us there remotely. Looking forward to seeing you in person at an upcoming conference future years. So the next speaker we've got is Robert Moore. And Robert, if you can come up and get set up on the lectern. There we go. So that's the HDMI there. That's it. And then I'll just get out of your way here. Okay.
or even though we've gone through things and seen
Full screen, Robert Moore, make co-host.
Okay, great. So, Robert, you're now a co-host, so you should be able to on Zoom do share screen on Zoom. So go to your Zoom call. Yeah, you need to screen share in Zoom. So you need to flick across to your. You go to the Zoom call, there's a button, share screen. That's great. That's just what we needed. Thank you.
Is it not? Okay, this thing's doing something slightly weird. It's okay, so hold on. Yep. Okay. Okay, there it is. Perfect. Yep. Ready. Yep. All right, so good afternoon all. I'm Robert Moore. I'm from Embry-Riddle Aeronautical University. I'm a master's in unmanned and autonomous systems engineering. And at this conference, I'll be talking a little bit about my continuation of work from the last conference in redundant uncrewed aircraft systems. So, wait, is it not sharing again? Oh, dandy. Let's see. Your screen. Let's. Oops.
That's good. Thank you.
Okay, there it goes. Okay. So in terms of.
See here. Looks like it's the secondary screen.
Okay, so let's see. I need to. Send. Let's see. No share. Let's try. Working now?
Yeah.
Okay. Right, so in terms of the presentation conference, so I'll be recapping what my project is about. I will be covering the challenges of essentially doing an informal process of going through the FAA's mean of compliance reliability analysis document for uncrewed systems. I'll be discussing the system architecture, the current system architecture I'm using for the tests, some of the flight testing and the anomalies and hardware failures that I've had. And then Philip and I will be doing a
discussion on some of the proposed future architecture designs involving Cube Orange, which I'm using currently, Cube Red, and then a few other different ideas using both types of processors. Okay. Let's see, is it? All right, so in terms of the project recap, I started this project under a NASA University Student Research Grant, and I was addressing two of the NASA AMRD strategic goals. The first one was a tertiary goal, which was transition to alternative propulsion and energy. But the important one was assuring autonomy for aviation transformation for things like uncrewed aircraft systems, urban air mobility, and such. And essentially what I wanted to do was develop a redundant architecture for beyond visual line of sight, EV loss, related operations, which for other high-risk operations like operations over people. In summary, having a single point failure which could endanger the public or their property on the ground, I deem unacceptable. So essentially what I did was take the Cube Orange hardware and ArduPilot, and then I added Lewis scripting on top to do a switchover logic from primary to backup. So this is the document. It is the means of compliance document for doing a type certificate of an uncrewed aircraft system. It came out around February of 2020. I'm not going to go too in depth into the whole document, but essentially it gives guidance into my process for how I did my reliability testing over the past year. So with this testing, I was pursuing the rural type certificate hours, which is 3 airframes flying 125 hours each for a total of 375 flight hours. What this does is it gives a good amount of flight data for the reliability of the system, determine what fails on the hardware side or the software side. Essentially, it dictates if the airframe is safe to fly, and if there are issues, how you mitigate them. And on the next slide, it shows some of the required conditions during a flight test. The ones that I follow the most thoroughly are the 3 aircraft. I don't cover the manual such because it's basic proof of concept avionics testing. In terms of the UAS, it's subjected to some of the worst case conditions in terms of in flight. I also have tested some failures like engine flameout and different arrangements. And that's essentially as thorough as I get because I'm not going through that full process. That would be outside the scope of my master's degree. And then here's some more background information. Excuse of all the text, but it really shows how thorough the process is. If you were to go through as a airframe manufacturer, trying to get the type certificate. So this is my current architecture design. So I took a model aircraft, the Seagull model Shot Cub. The reason why I chose this model was it's a fairly simple bush plane arrangement. It's also in the size of a 35cc engine equivalent. So what I've learned from some of my other airframe experiments, the Flex Innovations RV8, which was an electric low wing, had 2 short endurance. I then, for another project, had a 10-foot wingspan airframe, the Bushmaster 120. It looks like a giant turbo beaver. The problem is that's about 50 pounds, albeit it gets 4 to 5 hours of endurance. That would be within a certain scope, but when I was looking forward, I do want to do things like convert to quad planes. So phase 2 is the standard airframe. Phase 3 would be essentially doing vertical takeoff and landing testing of the redundant systems. If I were to do that with a large airframe, I'd be at 70 pounds. This airframe, I can be under 50 pounds if I incorporate in vertical takeoff and landing hardware, such as a pair of lift booms under each wing. On that note, the airframe did have some hard points to incorporate lift booms where the struts are, so that was another means of convenience. The airframe gets about 2 hours of endurance, which is fairly ideal. Once you get into the 4-hour mark on a single flight, it hurts a little from the operator on the ground perspective. And in terms of hardware, like my prior tests, I had the Cube Orange arrangement with the HERE 3 and the RFD 900X, the PowerBrick Minis, 2-cell LiPos to run all the systems. It's essentially a mix of CubePilot, and Jetty RC systems. The reason why I went with Jetty was the servos have telemetry feedback and it has central power distribution hubs that you can plug multiple flight computers into. On the propulsion system, I went with gas because batteries get really heavy and expensive when you're doing the long flight hours, such as 2 to 4 hours, and it's easier to essentially gas and go with the airframe. In terms of flight testing hours, I intended to complete a lot more within a year, but many challenges arose. Unfortunately, I did lose access to one of my big test fields where I could go day in, day out. So I had the generosity of a model aircraft field to do my testing, but it was a lot more restricted. Of course, being a master's student as well, you have all the other classes and obligations that you have to do. So within a year to get 31 hours, fairly respectable. And there were a lot of things which also got in the way of building up a lot more flight hours as well. So I know this is a terrible way to do a PowerPoint with blocks of tests. Essentially, these are to show that my airframe that I selected wasn't necessarily ideal. Every flight there is a problem, a part broke or some anomaly happened, so I couldn't crank out multiple flights within a day. So my intention was one airframe do 125 hours, next airframe another 125. Instead, I was chasing so many parts breaking on the airframe and a few other minor discrepancies. There's things like clevises failing and the struts failing, other metal hardware failing. I had a few engine bolts break. I had a few flameouts. It really shows, that going through the flight testing process, depending on the airframe, it can be a real bear if you're trying to get reliability data and everything is breaking. And this is the kind of data the FAA appreciates. We don't have reliability data. So this is a way to document and say, hey, this is all the issues you could have during sustained flight ops. And then to kind of sum it up, picture collage showing some of the different things so you can see metal hardware breaking in the top left. I had an engine gasket let go and it sprayed engine oil all over the airframe. Some of the struts, it was a screw-in arrangement and they stripped out, so I then had to JB weld them together. And then I've had blind nuts just cleanly break on the poor airframe. And I guess this is a better way to show it. So despite those walls of text and the photo collage, this kind of shows over the course of the flights my percentage of failures. Avionics were fairly reliable with exception to a rudder servo dying fairly early on. The engine bolts breaking. I was pushing the envelope on some windy conditions. I did have some fuel exhaustion events where it would essentially be in the loiter, flame out because the turbulence was excessive, and a 100-ounce fuel tank results in fuel slosh. So air bubble, engine flamed out, land okay. But the most was the major anomalies of the struts, clevises, metal hardware breaking. So the good news is our avionics are fairly reliable. It's the airframes that leave a lot to be desired, and that was a total of 31 failures and anomalies. In terms of some of my current testing as well, for my master's capstone, I investigate a line replaceable unit of the avionics. So this goes into one of the philosophies I appreciate, the right to repair. One shortcoming I notice of the industry is many avionics are incorporated into the airframe. If you have an issue with that, the avionics or anything in the airframe, you have to send the whole fuselage back to the manufacturer or have the manufacturer fly out. It would be a lot easier for both the operator and for the manufacturer if you could remove that avionics unit, pop in a fresh one and send that avionics unit back, say if there's a software or weird hardware bug, because as you know, testing only catches so many issues and Murphy's Law always comes back to haunt us. All right, so this is the current design. So you can see it's the two cube oranges, and then you have a RC receiver into each, a here, GNSS for each, an airspeed pitot, and then an RFD 900 for each. They go into the Jetty central box, which has, well, for this, I'm using 2 cell LiPos. Depending on what I do, I can have a pair of voltage regulators in line for higher voltage LiPos. And then the advantage of the Jetty, once again, is I take the Jetty Ditech servos and I get telemetry feedback. So if a servo has an issue, I can diagnose it instead of guess, did a servo fail? And then Philip, I guess you can then discuss some of the QBread stuff.
Cool. So, yeah, last year I obviously didn't get to come to the conference. I was otherwise occupied at the Formula One. But I did have the pleasure of listening to Rob's talk and got to have a bit of a virtual chat online on that one. And myself and Rob have been interacting ever since, and it's been great, especially how ArduPilot brings all sorts of different people from different places together. So, yeah, looking at the redundancy side of things, it's a topic all of us have been talking about for a long time, and it's been a lot of people do a lot of work on that. A core part of that is the work Leonard's been doing with standby mode and all of that sort of work, which without that, it sort of becomes really complicated and messy and a very ugly takeover if you don't deal with some of those iTerms and things like that. So on the QBread, we've gone for a architecture which is basically 2 autopilots in one. So we have a primary autopilot that basically does all the fun stuff like Ethernet and all of the normal day-to-day things, and we have a second autopilot that basically can do the simple things. So if you have something go wrong, you can basically package what Rob had done with the 2 cube oranges into a more convenient package. So basically, depending on how you do it, 2 doesn't give you the ability to start automating the switchover process. So the switchover process in all of this is very much the pilot is flicking to the second autopilot. And that's basically the mentality I think most systems at the moment are going with, of not trying to put too much guesswork into what is flying well and what isn't flying well. And we can add that complexity later down the track. So the idea would be things like a GPS is actually connected to CAN bus 1 and 3. And so, you know, therefore it's available to both autopilots. In the QBread, we have 3 CAN buses to give us access to every single bit on there. We'll go into the architecture of this stuff in probably a few months once we get everything tested and proven. But we've basically got an architecture where the I/O structure is separated from the FMU in a way that either flight controller can get access to all of the I/O that's available. The idea is to try and make sure there's not too many single points of failure. On the QBread, there is one big single point of failure that is still there, and that's the 5-volt rail. There's option for 3 going in, 1 coming out. As we often say to people, a autopilot is not a power supply. Please don't power silly things off your autopilots and manage your power well. But yeah. On this drawing, you'll notice there's 2 QBreads on the one system. And that's sort of an architecture we're looking at moving to. We'll be doing another carrier board for the QBread that actually does have 2 cubes on it. And we'll have the ability to have a completely independent power system on that. However, this is not the only way to do redundancy. And there are other ways coming up that might be a little bit more interesting. You could whack a whole bunch of distributed cubes around the place, which I think is shown in there with 4. That might be a convenient way. Or another way you could do things is things like our Here 3 Plus and our Here 4 that's coming up soon, Here Pro, actually have all of the components on board to be an autopilot. So rather than actually necessarily having everything in the little, you know, vibration isolated box, you can actually potentially be running an instance of ArduPilot on a node somewhere. So you could distribute it completely. This little beastie, which I've probably shown a few of you, is our little CAN bus node that we're sort of working on. It has enough power on it to run ArduPilot a few times over as well. So a concept of a more distributed autopilot system on a distributed CAN bus also can deal with issues like structural damage to the aircraft, taking out a CAN line or something like that as well. And can also be very convenient if you're doing a payload vehicle where you don't actually have a center to the aircraft. Yeah, So Rob's been doing some great work on that, and so have many people here. And yeah, Sid's been doing some great work on the upcoming architecture of the red, and it'll be really cool to get some of that stuff out and ready.
Now, to kind of bounce off what Philip has says in terms of that carrier board should not be used as a power supply. So there was something that came out in the RC community recently from a well-known company called Powerbox Systems, called the Powerbox Royal SR2, I believe. The one thing that really piqued my interest was for its new protocol system, P² bus. Not only did it have the servo outputs, which it provides power distribution to, it had 4 P² buses where essentially one could consider it like, I know this is a bad way to consider it, like a CAN bus node RC equivalent, where, or better yet, you know, the old S-bus hubs and nodes that you could plug in, except these have telemetry feedback. So I was thinking, well, potentially, I know that this could work. Why not we have something that's both the carrier board for multiple redundant cubes, but also then be a power distribution hub for, say, a giant scale airframe. So we're talking like 25 pounds, 30, 40, 50 pounds, you know, something like a 10-foot wingspan, you know, a larger Group 2, Group 3 UAV. That way you could run something like 16 servos and have that power supply, which didn't burden down a carrier board, and then have plug out auxiliaries for something like in my case, I was thinking a drone CAN power bus. So you could have maybe like 4 different drone CAN nodes, which could provide power to. It could then essentially, you could then have those drone CAN provide telemetry feedback. You could then also control camera systems, maybe have an S-bus out system. So you could then do a few different power distribution like the Jetty CB210. Then also provide power for things like the RFD. That way you could properly power an RFD, or maybe something like an L-Site Halo, which is the 4G communications. Then have plugins for something like 3 GPSs, 3 PIDOs, a wide voltage range, a LiPo for like 2-cell to 12-cell. Essentially give you various flexibility for a giant scale system. That way you didn't have to do like a cube and carrier board, followed by a power box system, and then a bunch of other random plugins. Just have it all consolidated into one central hub for simplicity when integrating it into the airframe. In terms of future architecture design, so part of my capstone was this line replaceable unit. So I'm thinking for 25-pound and larger airframes. So right now I focus primarily on a fixed wing standard airframe, but I began the software process in the Lewis scripts for switchover logic for VTOL systems, helicopters, multi-rotors. It does need a lot of refinement. You'll see in the subsequent photo why it needs refinement. And of course, I will admit this isn't a one-size-fits-all. I'm thinking of many different redundant architectures for different airframes. For example, where standalone avionics, where you put all that in an LRU, doesn't make sense as for, you know, a small 15 to 25-pound airframe. For example, something like a Make Fly Easy Believer, if you want redundant avionics, this would be terrible to incorporate. When QBred comes out, it really sizes things down in half and makes it really convenient. In this CAD drawing, I was experimenting with an ODD 44 connector. It isn't an end-all be-all. I could do servo plugs. I could do other things. You can see the I²C and the CAN bus plugs vertically. You can see the plugins for the RFDs in this experimental case. Because I fly in Florida and it's hot weather, I did have a full cooling fan arrangement just to play it on the safe side. But what I like about the LRU concept, especially when QBred and the dual carrier board comes out, you could then have flexible redundancy like primary backup up to quadruple redundant if you use 2 red cubes. For future flight testing, so right now I'm at a crossroads where I could replace a lot of the metal hardware on the shock cubs. and pray that they still stay together, because it would be nice to get that data to say 125 hours per airframe, just to see if I hit a steady state where no more parts break, or if I still have these issues throughout. If it really becomes a headache, an airframe that I want from the get-go, which wasn't available, is the Bushmaster 100. The Extreme Flight Bushmasters are incredibly simple, incredibly rugged. You can gas them up and go, and you can knock out a bunch of flights, and you don't have to worry about parts breaking left and right. And of course, the most important, which I do want to do after the standard flight testing, is an reliability test with quad planes, because there is a market push towards a lot more VTOL airframes. I believe this is the last airframe. Oh, no.
Video's good.
One other thing that I did, come on, let's see. Oh, there it goes, I think. So I did do a little bit of business development as part of my master's. So to provide some clarification on the video, so with the RV8, so the initial roll maneuvers was just testing primary to backup switchover, and the backup kill switching the primary. With the severe upset recoveries, that was me putting it in the worst possible case scenario, essentially deep stall, cover and maneuver, and the backup did the switchover, took it over. I had no input into that. And then that's what led, once it proved that it was reliable, that's when I switched to the shock cubs. And as you can see, beginning the VTOL process, but there's still a lot of work to do. There are many different states you have to account for, such as transition between vertical lift and horizontal. You know, what does it do in horizontal flight? What does it do in a standard flight and vertical lift? And that's just, the Lewis script just blows up in size as a result. In terms of concluding remarks, this is what I've learned over the process of the past year. The airframe has to be as reliable as avionics. Otherwise, you're going to have a bunch of headaches building up flight hours. Multiple avionic architectures are required, and having industry input and discussion would be vital. And of course, I do need to pursue further flight hours to gain reliability data. Let's see, I think one slide glitched out. I think there's one really important thing. So let me go back. I believe it's slide 3. So I do want to thank Philip Rouse and all of ArduPilot for all the support of getting me down there. They were essentially my sponsors for this conference. And I want to thank you, Tridge, and the ArduPilot community for letting me present again. This is really vital information, and I do like the open discussion of ArduPilot to discuss making our system safer so we can essentially do safer operations. I'd like to open the floor now to discussion of some of the different redundant architectures. I know some groups have been pursuing this. If you're free to discuss, let's have the discussion begin.
Can I just ask, Seppo, are you free to discuss? No. Probably not. Okay.
Okay. Yes, Paul?
so the question is that obviously if you have a two-lane system, probably you always got is how do you know that one lane's fine? Make a switch over and switching over all doesn't get it. So I think you alluded to that and just that's been done by the triplex with media select. Which is mathematically guaranteed to be robust to give first failure. Problem we have with our highly autonomous or automated systems with multiple state machines at multiple levels is that you can get a situation and be crazy where one flight computer is trying to last the hour and the other flight computer is trying to fly to waypoint 3 and the other flight computer is trying to fly to waypoint 7. Or the integrators on all 3 lanes to diverge. And then you switch over and you get a bad day. So that's in part of being handled by cross-level database. With those key items that it remains keeping on. But we need to include in our architecture, and that includes our software architecture and our hardware. We need a low latency data link. Those 3 flight computers or 4 are when you put in can actually share the synchronization data between them, and we can keep it synchronized so we don't end up with a lane switch followed by an aircraft that's flying in waypoint, while after the other suddenly try to fly back up and go to waypoint 7.
Exactly.
Yeah, I'm not quite sure what you've got in your. What links we've got available at hardware level for these nodes to talk to each other and. Sending data across for the critical process.
Yeah, so the primary link at this point will be CAN. And the SID's been putting a lot of work into getting CAN FD across, which speeds things up dramatically there and gives us a much heftier bus. And we have multiple CAN buses running. On the Cube Red, we also have a serial bus between the 2 systems so that they can do what needs to be done outside of all of that.
And even that we had actually run it like my like we wanted to run it 2 megabits, stuff like that. Because the same block and the same sort of block structures, they will see the connection data for the passes. So that's sort of data 80 plus serial that gives you a lot of that fishing and
because
but I think the implementation of this implementation itself is more of an architectural question for ArduPilot. That is more of that.
Because there are 3 types of synchronization data.
Yeah.
One state and which means we need to have a process of negotiated state change for the 3 nodes.
Yeah.
Then you've got your traditional integrators.
Yeah.
Which are things like controllers, your controllers. And then you've got things like states, things like that, which if one gets read, if you get a
the way I designed standby mode was it basically follows everything on a so it takes all the same inputs. So if you change mode, change topology, change it'll follow those modes, but internally it prevents the item build-up of position controls, attitude controls, and all that sort of stuff. So the thing is, so if you actually are, if for some reason you have a failure, that means that the autopilot that is not selected to fly the aircraft is actually flying the aircraft because you've got a failure in your servo outputs, in your servo output selection circuit. So you're actually locked on
that's another architecture decision.
That's right. Yeah. So so I wanted to ensure that if you failed there, that even though it was the unselected autopilot with its item 0, it could continue to fly the aircraft. It's just that it would tend to have a bit of lean error and that sort of stuff here and there and something. However, what that relies on is, as you said, if you're in an auto mission, you've got both of these 2 autopilots running the same auto mission. However, the autopilot that's not controlled may think it didn't quite reach the waypoint yet, so it may not trigger the next waypoint. So that's where the overriding thing needs to actually pass that information.
State changes, waypoint.
That's right. Yeah.
So each element, each node. So I have an intention to change, make this change.
That's right.
And it wouldn't go like democracy, it would wait until somebody else, another, and until the majority of elements agreed with it.
Well,
And
that's,
then you make a change. But then if you can't get agreement between three and you got unparliamentary effect, then you revert back to a default. Which is a safe fallback. If nobody can agree, then you're going to agree to do this.
well, then you're actually part, that's it's a whole level of complexity again there.
This is not something that's.
Yeah.
I think baby steps are important in this too,
Right.
the ability to manually switch between this and this. In the examples that Rob used, the aircraft is flailing around in the sky and the pilot goes, oh dear, this doesn't look good. Flick into something that puts it into a mode that is safe. And that mode could be simply loiter, and that autopilot might do nothing else other than hold it in position until you figure out what's going on. So keep it safe, keep it simple to start with. And all of this stuff, we definitely want to get there, but step by step by step.
The point I was making there is, the state is starting to talk about passing around there are actually internal navigation decision-making mistakes, in which case a single autopilot can no longer make a decision that
That's
it's.
what we've done, you don't do it this one. Essentially, you've got three pilots in the top that.
That's right, whereas, the system that I envisaged with the standby mode, that all that is being done internally by one autopilot, and then the others are kept up to date with that in case they get
So
switched.
it's not guaranteed by already on any single plane. That's where we play the same.
Right.
Yeah, it depends. It depends what your outcome is. If your outcome is to finish an auto mission, that's a pretty complex thing. If your intent is to stop, just be safe, then that's a good starting point.
What
Right,
we're
and
talking
to-
about another level above.
It's like, it's a bit from already, this is stuff like.
Right, and just to provide some clarification in terms of what my system does currently, so the backup flight computer through the Lewis script sees an exceedance in parameters, kills the primary. Goal number one is to auto level the airframe and get it to within a cruise speed. So if it's overspeeding, it slows down. If it's stall, it speeds up. Then it goes into either an autonomous loiter near the launch point or at RTLs. So just starting with the baby steps. As you said, continuing the auto mission, that's a whole nother layer of complexity, which,
Yeah. We define, we just need to be clear what we're trying to do, what we're not trying to do. Because
right,
the concept is this is a part of operating system where we can continue the mission. That's very different to a system where we get it down in a safe way. Finish the mission in a safe way.
I guess, do we have a redundancy systems thing in the Discord? Maybe the next logical step is to say this will be our phase 1, 2, 3, 4. Start simple, build it out, because right now primary backup, it's better, but it's not perfect to say a triple or quadruple redundant. And then we slowly want to make that more capable, like you said, as time progresses.
Yeah, so there's a reason we actually went for double. We were originally going for triple. The reason we went for double is because baby steps.
Because you do that, switch out, which
Yeah.
still currently used in the aviation industry, but things like that.
Yeah, exactly. Yeah.
I guess this has been to the weeds. If I added my scripts on top of QBread, could it then do it automatically instead of a manual pilot does a switch?
And that's that. There's so many cans of worm in that one that it's many more talks and many more meetings, I think.
Yeah.
Like this is in continuation with the same. This redundancy, does it work in the master slave mode? Or I just wanted to know how with the handshaking it done between the two flight controllers.
So in the current setup, the second one would be in when it's standby mode. Basically, it would be sitting in standby mode, and you would say this one's in charge, this one's in charge. That's step one.
Well, that's only for the multi-rotor code. So the plane code has a different set of. Yeah, there are differences between the multi-rotor and the plane issues as well. So.
So in case of copter and one plane, suppose we are having two flight controller. Okay, so they are working in redundancy. In that case, what is the handshaking will be done within the group call during runtime? Both will be both will be having the same state, but each IMUs or the peripherals which are connected, maybe they may be reporting the different data. So how is the handshaking then between the two flight controllers? And does our ArduPilot, does it support this redundancy?
I think, Leonard, do you want to answer that one?
Yeah, so, standby mode takes care of, offsets in attitude, position between the two autopilots. So one autopilot thinks it's flying here and dead over, the other one thinks it's slightly canted off and, a few meters off. This autopilot's going to want to make corrections. This one's happy. This one's in control. That's why it's happening. This one's not in control. So it's by default not getting what it asked for. And it's not going to be happy. Standby mode basically says, we know you're not happy exactly, but we're going to remove your ability to build up those items and integrators. That would mean if we switch to you, you have a huge step. And so what happens when you, because those are all kept small, the aircraft starts fighting from the moment you get that autopilot starts fighting that offset from the moment you switch to it and builds up then, rather than it has this massive built up item that it can't do anything.
Yep,
and so this just basically allows you to so that all that internal state is sort of handled inside. And then the stuff that the only time you need to sort of synchronize then is if you're doing the more advanced thing, like keeping the two navigation controllers on the same leg of a waypoint and that sort of thing.
Yep, and to kind of bounce off what you said with the whole iGain thing. So in the early days of the RV8, I made the mistake to put both in auto for ArduPlane. The iGain ran away and then all hell broke loose when it deflected controls to Maxon and she went essentially, out of curiosity, is there a standby mode for ArduPlane, or can it be?
Not that I'm aware of.
Okay.
I did standby mode for Copter a few years before because I knew people were going to start wanting to do this sort of stuff. I was hearing people sort of become interested in this. And basically, I didn't want to be dealing with people crashing aircraft. So I built this little state in there that basically made everything safe so that people like yourself would come along and then start building all the issues on top of these things and start to produce the specification to take it to the next level.
So in terms of that, I did do a bit of limited testing and ground testing for Copter. The good news is that does work as intended. In terms of what I'm doing with plane right now, I'm keeping it to the manual flight mode, just so nothing gets deflected. Buzz, you have a comment?
I was just going to say, for plane, you might be able to use Lure to zero your items.
Oh, maybe
I think the work Leonard's done on Copter really paves the way. So it's a matter of stuff like
this effectively, sensibly, like there are a whole heap of things that are effectively integrated. Some of them are more subtle than others. There are the obvious items, but there are a lot of position velocity controllers that actually are effectively integrators that need to be, that maximum positional errors need to be limited and things like that. So, so there are the easy things, but planes also tends to be a bit more point and shoot in its navigation too. So you can probably get away with, it doesn't have the tight position controller, it's got cross track. And it'll probably handle a cross-track arrow being kicked in quite cleanly anyway. So you can probably get away with a simple Lure script just keeping those items set to 0.
Sure. Yep.
So when we say the redundancy of avionics, do we mean the redundancy of sensors or the microcontroller?
in this circumstance, we're talking about the microcontroller. Normally, for the last few years, we've obviously been talking sensors. Cube's been triple redundant on the sensors, but the single point of failure has always been the microcontroller. And that could be a mechanical failure, it could be an electrical failure, it could be a software failure. lots of potential causes for something like that to happen. So
did we encounter any microcontroller failure in this, and were we able to recover from it?
So it wasn't a microcontroller failure per se. So the DA35 has a lot of vibrations and it does beat the airframes up a little bit. So one of the flights, I had the primary flight computer, the cube came slightly loose because the screws vibrated. Fortunately, flipped to backup, land no issue. Carefully removed the primary, tightened things back up, did some vibration mitigation measures and went on my way. So more of a airframe induced hardware issue, but not the hardware failing itself. Like that was a user installation error, not a physical hardware failure.
Rich, I believe you've got some tests and things you can be very nasty to flight controllers if you want to be as well, don't you? That we could do horrible things in flight. So obviously, when we get to that point, yeah, we'll be very mean to the thing. Yeah. So.
Okay.
Cool.
Yep. Yes.
Just a comment, if I may. So if you split up your testing across 3 aircraft to achieve the FAA's 350.
That was the attempt. So I'm still on airframe number 1.
But my comment was going to be that very sure that the rules are that it has to be 1 aircraft because you're trying to achieve 100 hours.
The FAA's requirements are actually a minimum of 3 aircraft to achieve
Right.
the hours.
And
So that's
though
actually one of their requirements.
the airframes do have to be set up identical,
Yeah.
so same firmware, same hardware. So if I go back,
So your goal was to achieve 175 hours on 3 aircraft, not 175 hours between the total of 3 aircraft, is that correct?
correct. So it's 125 hours per. Yep. Yep. Any further comments? Yes.
So this is in continuation with the previous question only. Since told that there will be standby mode. So when it switches over to the other flight controller, when it switches over to the other flight controller, so that switchover time, whether that copter will survive for that much of time.
It's instant.
Yeah. I'll put it this way, I mean, we're throwing images out of horrible things tumbling and they survive.
Yes.
Yep.
The 2 red ArduPilot, are they identical or they different as similar in sensors and architecture?
If we run 2 of them, the 2 will be the same, but there's a bunch of different sensor architectures within the one. There's 5 IMUs in the one. I will say they're all InvenSense. Yeah, but we have 5 different sensors in there. And there's less sensors on the secondary controller to the primary one. So that there's definitely going to be a difference of behavior in there because the secondary one doesn't have things like the Ethernet and a few other. It doesn't have an SD card. It doesn't have USB. It doesn't have all this other stuff. So there will be a difference there. There are some other architectures we're toying with, but this is an ArduPilot conference, so I won't mention PX4 on one core and ArduPilot on another. I'm not sure that would be appropriate.
Just curious if they drive the requirement.
Sorry, what was that?
If they drive the requirement for the cubes to be dissimilar.
The FAA want evidence that the thing's not going to fall out of the sky. It'll be up to us to figure out how we do that if we decide to go for a certification.
The problem about the sufficiency.
Right.
And I define the problem.
Right. And I will make a fairly big disclaimer. Like I said, I'm not formally going through the process. As you can see, this is for the airframe and not avionics per se. I don't, besides the DO standards, I don't think there's certification for avionics.
The FAA, CASA, and many others are sort of going to different methods of proving reliability. There's definitely there's definitely benefits in some testing and stuff like that, but in different ways. But we've really got to get them defined, and it's really up to each individual group. We've got multiple companies around the world that have already managed to get FAA certification with our cubes and ArduPilot and stuff on board. So up to the end user really to actually define that and finish that off. We just give them the tools.
Thank you.
Yes.
So operationally, the flights, how did you perform them? Because I noted that the times weren't really different. So did you perform the same mission over and over with automation, automatic takeoff and landings? Or were you doing something like that?
All right. So with the shock cub, I prefer manual takeoff and landing, but I was doing autonomous loiter. That was due to a constraint of being on the RC field. It's under a letter of authorization in controlled airspace. So I kept it within a fairly confined area just to loiter to play it safe.
Yeah, I was asking this because the repeatability of and the stress, mechanical stress over, pilot errors, landings or something. Or, the limitations that come with automatic landings. Yeah.
Right. And I didn't install things like LiDAR stuff so that I had a financial constraint under my grant. I'd also done a change of scope to go to the gas airframes over 3 RV8s just to get the endurance. So I've essentially run out the budget within my research grant. So when I decide to pursue the next phases, I would need to seek capital to, do a VTOL conversion or change airframes or such. But fortunately, my university has really great avenues for pursuing funding. Yep. Yes.
Yeah, were you able to close the feedback on whether secondary probably like a two as well?
Oh, sorry, can't quite hear you. Could you speak up, please?
Were you able to confirm like when the secondary flight controller was the control, or was it just a loop booted switches?
You said close.
Can you confirm? So I'll just translate from British to Australian.
Sorry, my hearing is a little shot. Gas airframes are terrible on the
I think he's got a microphone now, so. No, microphone not. No, sorry.
Yeah, just.
He just wanted to know if you could if you got feedback.
Oh, yes, I did. So the Lewis script says, so essentially I have two things. So it says backup has taken over, but the nice thing about the system is if I want to cycle through multiple failures at once, I can then re-switch back to the primary. So I can say primary reactivate or backup has taken over, or I can just do it via the switch. So the pilot can do it or the system can do it itself. And it always confirms, assuming that I get an accurate RFD downlink. Yep.
With the aircraft that was selected, it's got lots of parts on it, obviously, and things going on. I was pleased with a 5-minute run with one of their motor, feedback and packing it, and the 3 servos. And that they're the problem system is you can get them to fly 2 hours and they're very reliable.
Granted, it's a little simple. So part of the reason I chose this airframe as well is it's 1 servo per surface. So if I had it, so for example, I had a single servo failure, it didn't take down my whole airframe. So from the last talk I gave an example of a single elevator servo on that airframe. That servo burned out and then went the airframe. So this is a good proxy for, a servo per surface. So even if one failed, like I did have one fail, I could still fly it back.
Well, one form of reliability right now.
Right. So it's essentially, you can keep it simple, like a quad rotor or a single servo per surface line simple, or you can add redundant elements to a point.
Yeah, I would agree with that. There is a tendency to tend to want to have the fanciest test equipment out there. A good old Bixler 2 or something like that is a very good test point. It's
that's
not quite as pretty, but yes.
And for what it's worth, I mean, there is a group out there who does have large bush planes for some of their flight ops that they've converted with great success. I mean, initially I would have done the Bushmasters, but things changed and then I went to the Shock Cub. So that was a design decision I made. Yep. All right. If we're closing out, I do want to say one final thing. Last year I had 14 companies reach out. I want to thank those companies for reaching out last year. Some of them I've maintained constant talks with, which have given support and ideas. Unfortunately, there were some that sent emails, which I sent emails back, and I'm not sure if it went into the void or such. So before I fully close out, just on the off chance that there's some kind of email issue or such. So I have 2 email addresses as a primary and backup. Feel free to reach out to me again if you never got a response back, and let's see if we can get communications going. Also, LinkedIn is a good way to find me as well. So thank you all for your time, and thank you all for the discussion.
Great to see the development over the last year, Robert. Oh, we have, yes, you already.
Yeah. Okay, and we can go sideways here. Cool. Arrow keys work.
Nice.
I don't know. This mic is connected to Randy's.
That's
computer?
right. So
Okay.
that mic is the one you should be muted. And then his mic gets started.
Cool.
Great.
All right. Should we wait for a few more people to sit in?
I think when you start, if you start talking loud, people will sit down.
Yeah.
But I can.
Yeah. That's okay. I'll just wait for.
Yeah,
to get down to start. The broken headphone.
So, the final talk for, the Friday afternoon session, is we have, Blue Robotics, William and Elliot, each giving us an update on their Blue OS system. Over to you guys.
All right. So last year, William presented our basically initial start on BlueOS. We've made quite a few changes from then, but there's also some awesome features that were there from the start that we'll just cover briefly here as well, just to make sure that if you haven't seen that, haven't come across BlueOS before, you get a sense of what's in it. But the focus of this presentation is on what's new and sort of what we've made available now. So just as a quick overview, we'll be going through why we made BlueOS in the first place and how we've been going about the development. Then William will talk through how BlueOS integrates with the ArduPilot. Then I'll cover some additional functionalities in BlueOS that are kind of outside the realm of the ArduPilot, but still useful for the vehicle and for the operator. And then William will go through how BlueOS can be extended by users and developers and the like. So just starting out, Blue Robotics is a marine robotics company where, well, William's the primary maintainer of Ardu Sub, and the sub vehicles that we use rely heavily on onboard and companion computers for video streaming, flashing the ArduPilot. We have enclosures with the ArduPilot in it that aren't always great to open, especially if they're, 1,000 meters under the water. Then Mavlink pass-through down to the vehicle, including for joystick inputs. We often use a tether, telemetry data going in both directions, parameter setting, things like that. And then also fetching logs from the ArduPilot. As mentioned, if your ArduPilot is in an enclosure that you don't want to open, then you have to kind of get those logs out somehow. We also use a lot of different third-party sensors. They're not all ArduPilot specific. Some of them are quite high bandwidth and aren't particularly relevant to vehicle control. So it's not super important for the ArduPilot to know about them or to operate with them. And that includes like environmental sensors like conductivity, turbidity. If you just want to have some scientific measurements that you're like, well, ArduPilot doesn't care about this, but we want the data. So our initial solution when Blue Robotics started and tried to make a vehicle was basically just a forked and very highly modified version of the ArduPilot companion software. That's quite monolithic. It's sort of one thing that's tied together. And because of the extensions and things that we wanted to make to that, it was difficult to maintain, especially because different people wanted to work on different things. And the needing to fork the whole thing to run it on one vehicle made it hard to sort of share across vehicles while having changes from multiple people at the same time. We also have just in general people who want to integrate different sensors, different actuators and the like, and they sort of need an ecosystem to, for them to thrive, they need an ecosystem where they can kind of easily develop their own components. And that has to be in a maintainable way and a way that can be shareable across vehicles without having to sort of fork the entire thing that everyone is running. So our target market for BlueOS is just anyone who wants to make or use an advanced robotic system. That includes developers, which is, all of you plus very many people, users of our vehicles and any other vehicle that uses BlueOS. It is open source and is not intended for just marine robotics. So user base can be quite broad. Integrators of sensors, actuators, cloud services, whatever, and educators about advanced robotic systems as well. The sort of underlying premise of a BlueOS system, we're assuming that there is some kind of Linux-based onboard or companion computer available. There's network connectivity. BlueOS uses a lot of web-based things. So ideally, network connectivity is always available, but if it's at least available during configuration, then you can still use our sort of configuration tools and the like. And then a Mavlink compatible flight controller. We generally recommend ArduPilot firmware because it's what we work most with, and so it has the best integration, which also works well at this conference. So just as a quick overview of an example system, so you'd have a flight controller board. That's a navigator that we make, or you could have a Pixhawk, whatever you want. BlueOS will just talk Mavlink to it, but flight controllers like a Pixhawk, we can flash the firmware onto, which is a kind of nice bonus. And that will have connection to the actuators and sensors that are relevant to the vehicle control. Then you'll have your onboard or companion computer. In our case, that's generally a Raspberry Pi, but BlueOS is made to be able to shift over to other systems as relevant. And you might have some environmental sensors or maybe some cameras and things like that that are attached or plugged into that computer. And then there's some form of network link, potentially additionally Mavlink, but yeah, so Mavlink might go separately or just through the same network link. And then William.
So after kind of trying to leave behind that monolithic system that was our old companion, we had to do some design choices. We ended up choosing to have containerized components with multiple individual services, as tiny as possible, basically microservices. And we also allow integrators to create their own extensions, which are basically individual containers that run alongside our core container that is actually BlueOS. So it's very easy to extend things, and we have proper APIs and an interface to integrate everything nicely. One of the advantages of using containers is that the dependencies are always isolated, so we can easily port this over to a new board or anything. And we can also limit hardware and resource access by extension, so we can have processing limits. Say you can only use one core of one CPU and 256 megabytes of RAM.
That kind of thing is particularly relevant if you have, so in our case, the Navigator flight controller is a hat that sits on top of the Raspberry Pi. So the ArduPilot firmware is actually running on the Raspberry Pi, and you need to make sure that you have enough processing available that you don't randomly lose control of your vehicle because something else took too many resources.
Yes, the extensions need to be tightly controlled so things don't go out of hand. We choose to work with web interfaces and APIs. So we have lots of services, and all of these services, they have Swagger APIs. So they are very easy to work with for developers to integrate new things. We're planning to have a main dashboard where we can show lots of information together, have an overview of the system. That's not quite done yet. And we also have planned to have a pub sub architecture. I guess it's similar to what ROS has, but it's not quite the same solution. It's still on the works. Our plan is to have synchronized logging of arbitrary data types. And with our extension manager, it's easy to install and share extensions. Yes, that's it. Next. For the front end, we picked Vue.js. It's a recently new JavaScript framework that allows for very reactive components. One example is we can animate a heart icon with the heartbeat, which is very nice to see when the vehicle is okay. It's easy to reuse components. And we use Mavlink to rest in the backend as a backend to actually talk to the vehicle, it's written in Rust, so it's very efficient. It was designed with modern technology, so we're based on Python 3.9 and with some people pushing for 3.11. All the critical services and The ones which need performance, they are written in Rust. And we use Mavlink router for Mavlink routing, but we also support Mavproxy, but Mavproxy is a GCS, not router, so performance is not great.
All right, so system components, just as a quick overview. You've got your Linux computer. There's a BlueOS Bootstrap Docker container that sort of starts everything up and also monitors the core container. So if something goes wrong, then it can start things back up and make it so that your system at least restores itself. The core container includes our core services. So there's a variety of services there that we'll talk about in the later slides. But one of those services is the extensions manager, and that's in charge of starting up and managing the extension containers. So for example, if you created a self-contained device integration container, the extension manager is in charge of starting that up and making sure that it doesn't go AWOL. That then leads into the front end, which is sort of web browser based, which makes it device agnostic. So if you've got a mobile device, you can view the interface. If you've got a computer, you can view the interface. You just have to end up connected to the network somehow. That interface has a sidebar that shows all of your pages and services that are available. And that includes if you've got an extension that you've created, they can kind of hook into that and end up as part of the sidebar shown there. The heartbeat icon that William's mentioning just before is shown up there. So you can kind of see it flashing, and that is actually tied to the heartbeats from the vehicle. And in general, there's other just convenience features there, like configuring your networking controls. You get warning icons if your system is overheating or things like that. You can reboot the vehicle, and there's also a sort of regular versus pirate mode view option. So you can see there's quite a few different services in the sidebar there. All of the ones with little pirate icons are kind of hidden by default. So a standard user who doesn't need to do any development or isn't trying to do anything crazy can just sort of work with their vehicle in an intuitive manner. And someone who needs a bit more power can just turn on pirate mode, gets a bit more access with the knowledge that they're accessing more powerful features that could do damage to the system if used improperly. All right.
Okay, so what do we have for ArduPilot integration? We're able to show all the firmware information, so which version, which frame, which actually firmware, so rover, copter, sub. We can start, restart, select ArduPilot. We can actually, BlueOS actually supports running multiple boards at the same time, which could be not very useful at a first glance. And we can also run zero on board. I guess it's similar to hardware, like zero in hardware, but it's actually running on the Linux board. We can flash firmware. We have a nice interface for downloading everything. We can browse logs. We can see Mavlink data. We can manage Mavlink routing, and we can do peripheral setup. So this is the interface for actual flashing and switching boards, where you can say, hey, I don't want to run the navigator now. I just want to use zero so I can test something. Another cool feature we have is that we can actually map ArduPilot's serial ports to USB serial converters. So we can use, let's say, a USB GPS and connect it straight to ArduPilot running in the Pi. We have a in-browser parameter editor, and it supports most of the metadata like step, bit mask, options, range. It also has some fuzzy hash, which is helpful. So this is us editing a bit mask. We have log viewer embedded into the flight controller, so even with no internet, you can still analyze logs. You don't get like map tiles, but you can still analyze everything and see all the plots. Okay, and we are working on downloading files via MavFTP for when we have, let's say, a PixHawk or a Cube ArduPilot. For Linux, routing logs is insanely easy as they are in the file system, so they are always easily available. For MavLink, we have a nice tool for MavLink routing, which we actually use it at the boat, like the lake test, to forward MavLink to Randy's copter, which was pretty trivial and a nice demonstration. We have a MavLink inspector, which can right now show all the messages and all the data, but we are working on actually enabling real-time plotting of data, as you have in MavProxy. This is the vehicle setup view. It has a 3D model that's easily, it's easily overridable by either users or, let's say, our distributors or anyone who wants to work with it. We have a lot of data there. We have the vehicle frame, firmware version. We have all the sensors detected via div ID parameters. We detect our ping devices, which are sonars. In this case, we have both rangefinder and scanning sonar detected. The goal here is to continue working on vehicle setup and get everything, get all of the setup necessary within BlueOS. So we have like motor test and we have sensor calibration and other tools. You've probably seen this guy already.
There's one down there. Yeah, we're releasing a boat soon. Some of you may have seen it. This is just a quick display that, like, yeah, you can switch out the 3D model, and that is kind of detected based on the firmware that you've got available. So
yeah, it's detected based on firmware and frame. So we actually have frames for all kinds of ROVs and adult, and I want to get frames for quadcopters and the other copters, but there are a lot of them. So
work in progress.
Okay, so for vehicle setup, right now we have only motor test and output assignment, basically. It may sound trivial, but it's important for ROV users because half of the support questions are people who, hey, my ROV is going the wrong way. So they have the motors wrongly assigned. And this is also easily overridable. We just have to create the model right, and we have instructions for that.
All right, so some of the additional functionalities, there's, as William mentioned earlier, the services that we're using generally have REST APIs. We also allow updating the version of BlueOS itself, and we've got quite a robust system for doing that. Video streams, generally the ArduPilot doesn't need to know about those, but we still want to see the video while we're operating, especially because that's one of the main ways that you can control a submarine vehicle that's, you know, not visible because it's in the water down deep somewhere. We also have USB serial routing, injection of NMEA, a file browser that allows you to access the files in the Linux file system, a browser-based terminal, testing of the network between your sort of control station and the vehicle, information about the system on the vehicle, and then some more information about the extensions. So the REST APIs, as William mentioned, have Swagger UIs that improve, or like make it easier to interact with them. So you can actually send API calls just from our helper service to just like test them out if you want to. And that's the same for if you, as an extension developer, create an extension that provides an API that will appear in the same place and can be tested in the same way. The service probes all of the open TCP ports. Any of them that respond to a HTTP probe are detected and then are listed in the available service list. And services can also like register themselves by providing a register service endpoint with particular metadata in it, and that then allows them to hook into the sidebar and provide a web interface page. There are also some more internal developer-based services that aren't really user-oriented, so they don't have external interfaces, but developers can use them. So there's the Commander service that allows running arbitrary bash commands in the core Docker container. And that provides access to the Linux system underneath using an HTTP API. And there's also the beacon service, which allows configuring MDNS network advertisements. So we generally connect to the vehicle using BlueOS.local as a sort of broad option. But if you're using a Wi-Fi connection, you can use BlueOS Wi-Fi.local if you're just on the same Wi-Fi network as the vehicle. And you can also set up custom ones for different extensions and the like. The version chooser, there's a bit of a GIF here of a version being installed, but basically the default interface is just if there is a more recent, similarly stable version of BlueOS available, it will come up as a button that you can click install and update. But if you're in pirate mode, you have the access to see all of the versions that you've installed previously that are still on your system, and you can switch between them. So you can go back versions just as easily as you can upgrade versions. And you can also change which, so you can install new versions from the list of full available versions, including changing to a custom remote. So if you've decided to do some development on your own while you're testing things out, you publish your own image, you can change to that remote and just install your own version of BlueOS instead of having to use only the official ones. And once you install, it will Bootstrap basically kicks in, switches you to the new core image, and then you're now on your new version. So you don't have to restart your vehicle to do that. Well, the autopilot restarts, but the vehicle itself doesn't. And that's the pirate mode interface there, changing the remote to Williams one.
The GIFs are out of sync.
Oh, okay. All right, video streams. We have a Mavlink camera manager that supports streaming from multiple cameras via USB that get exposed as individual Mavlink components. So that's quite useful for sort of tying them into control station software like QGC that just goes, oh, look, there are Mavlink cameras available, and then it can switch between them pretty easily without having to know about them in advance or be manually told where they are. We currently have UDP, H.264 encoded support, RTSP support, and WebRTC support. And we're also able to advertise external RTSP streams via Mavlink. So if you have an IP camera that presents itself with RTSP, we can sort of hook that into our Mavlink camera manager and present it via Mavlink to a receiving system. We also expose the video for Linux camera controls. So if your camera is a USB camera that's providing those controls, then that gets presented via Mavlink, which means QGround control, for example, can control your camera brightness, and you can also control that from the browser in the camera manager. We have plans for on-BIF discovery and also plans for supporting onboard recording onto the SD card on the hard drive or whatnot on the onboard computer. But those are yet to be implemented. There are a variety of other services. William spoke about them in the previous one, so we won't spend too long on them. But there's a bridges service that allows you to convert serial devices into UDP ports, similar to SOCAT. That's used under the hood to power our sonars, but can also be used for just arbitrary things that you want to get a serial device, send it to the top as some kind of network thing instead. The in-browser terminal has a TMUX session by default. It allows you to escape the Docker container, so you can go from the core Docker container down onto the underlying system and change things if you need to. So there's quite a lot of developer power and freedom there, and we're building developer tools into that to make it nice to use and develop on the system itself. The NMEA injector takes NMEA strings via UDP and then sends GPS input messages to the autopilot through Mavlink. So if you have a NMEA GPS that's USB based, for example, you could use navigators
Great. Okay, you're now a co-host, so you can start recording.
Hey,
Let me know when you're recording.
is it synced?
Yeah, I think it's back down.
All right, it's synced. Nice.
Good, we can continue.
No, it's out of
Sorry.
Okay,
Yeah,
go ahead.
it was already slightly delayed.
Right, audio and video. Yeah. Right.
All right, so picking back up. All good? All right. Okay, picking back up. So yeah, the active process manager or monitoring is quite useful for seeing if some service or program is using more resources than you expected. For extensions, we limit those like on a per container basis, but if you've got something in core that goes wrong, then you might end up with resource usage that's unexpected. So that's quite helpful for debugging. There's also a networking page that gives you information about your IPs, and it also tracks some of your bandwidth usage. So it tells you how many packets you're receiving and sending to each IP, which is useful if you want to know if a network device is actually connected and working. There's dmessage output for kernel and device information. So that registers when new devices plug in and get disconnected. So kind of handy if you want to know, why is this not showing up? Oh, it never even showed up in the kernel. That's neat. There's also information about the computer firmware. So the Raspberry Pi OS version and the BlueOS bootloader version that's running. And then the down below that, there's information about the Linux kernel that you're running and the system time. And then all of the information in the system information is made accessible to other services if they need that. And that's via our Rust-based Linux to REST API. So if you're writing an extension, it needs to know about something to do with the system for, convenience, or because it's critical to what it's trying to do, then it can access that via our API, which is a bit nicer than having to make all of the system calls itself.
Okay, so let's get back to talking about extensions. As I mentioned before, extensions are planned to be a big part of our ecosystem, since we have many different integrators and distributors who want specific functionality that we don't necessarily need in core. This is what it looks like right now. We have a small store with some examples, and I think 1 or 2 companies already chimed in, and it's like early alpha, so it's subject to change and it's not quite finished. The UI needs some revamp, but that's the basic idea. You can see resource usage and basic data. The settings are actually Docker settings. Is where you can actually limit what your extension is able to access and do. Okay, we will eventually allow searching with tags and tagging extensions and etc. The extension structure is pretty basic. You need a couple of small things. This is is a basic example to toggle a GPIO on the Pi. So you need some static HTML files if you're going to have a web UI, which in this case it does. It's just a toggle, but still web. We have register service, which is an endpoint that makes it just pop up on the side menu. Install.sh in this case installs some other requirements, which is in this case Pi GPIO to actually controlling the GPIO. And the README file is actually displayed in the store. When you select each individual version, you can see the README for that version of that extension. And the Docker file, which contains metadata and the recipe for building the image. This is an example extension that people use. It's a driver for water linkage DVL, which is a Doppler velocity logger. It tracks. It's like optical flow, but underwater with sonars. And since this is now uncoupled for BlueOS, it's easy to maintain it independently of us.
Yeah, so that one was originally built into our previous companion software, but understandably, it's a DVL from one particular manufacturer. Not everyone uses a DVL, not everyone uses that manufacturer, so it's nice to not have that installed as a requirement. But if you actually need to use it, you can just install the extension for it.
Okay, so this is another extension we are working on. Oh, okay. I thought it was going to pop up later. It is a GCS we're working on. It's web-based, and it's designed to be modular. It uses WebRTC for video, and it's not released yet, but there are some builds available for testing. There's just the other ones. But I lost my mouse. Oh, it's okay. Should I skip part of it? So yeah, each of these individual components, like the depth marker, the virtual horizon, the top bar, the compass indicator, they are all individual widgets. Our goal is to have a very modular ground station that people can customize as they want. We can have multiple videos. Yeah, next. Can go to next. Yeah.
I jump on.
Yeah, this is an example of how it's managed. You can select and edit each of the individual components. You can add new ones. You can have individual profiles for each of them. I think he has a video. This one, right?
Yeah.
So here we are adding a new video. It's a fake video stream, but oh yeah, there's a cat. Mandatory cat tax. You guys can move on. Mouse. And okay, move on.
Click on the slides. Yeah.
And since our controllers are mostly based on joysticks instead of radio transmitters, because water and radio don't mix well, we had to come up with a solution for actually mapping things better. We had many issues before with QGC and the SDL mappings going wrong.
So yeah, in this case, this is setting up a new controller. Just clicking on a button, pressing the corresponding button on the controller and just mapping that to the correct place so that it doesn't need to deal with like manually lining up the numbers. You just go, that's the one I want to press it, and it knows which one you're doing.
So there are actually two different mappings. There's one mapping from joystick to default inputs and then default inputs to functions. And we will supply most of these default ones for non-joysticks as Xbox, PS4, etc. But if someone is working on a custom joystick, as it's normal in the ROV world for reasons, they want things to look rugged, so they make it their own. So it makes very easy to map things. And yeah. Okay, this is an example of a cool extension. It's just a wrapper for virtual here. I'm not sure if anyone knows it, but it's an app that allows you to share a USB device over IP. If you look at the Docker file, it's just a lot of labels for metadata that we consume, and it downloads virtual here and starts it on time for. No, what? I want to talk about it more. So what it does is that you can easily just plug, for example, an ultrasonic sensor that's USB, like a rangefinder that was not designed for an ROV at all. You can plug it there, and then you can just open it on your computer as if it was plugged there. It's pretty magical, and people should try it. This is another cool extension that works very well with virtual here, zero tier. It's like a VPN. So you can just install this extension, and then you can control your ROV from anywhere if it has internet. We had one of the guys at the office in LA piloting my ROV in Brazil using Cockpit. and it was pretty cool. And okay, do you take over?
That's fine.
Okay, and we have this covers most of the features we have right now, and we have some other planned features. We want to do onboard video and audio recording. We don't have that yet. As I mentioned before, we want to do multi-source logging synchronization because we have to synchronize multiple videos to the log to all the Mavlink or like data flash log data. We want to improve the debugging tools. We have already GDB in there, so you can actually upload a firmware with debug symbols, and you can connect GDB to it and have like debugging your real hardware instead of zero. We're planning on support multiple other PIs. I mean, single board computers like the Jetson or Banana Pi, Orange Pi, those individual things. This is for BlueOS, not necessarily Navigator, because the pinouts are very important. And we also want to have a like web Mavlink console just to make like MavProxy, just make things easier to play with. And you can try it. You can download it with this link. Just scan the QR code. What? It's BlueOS is open source. It's on GitHub. We are currently using Dogger Hub for the images, but as you might have seen, we will probably expand for other registries very soon. And I guess that's it. Any questions? I expect many.
Of the OSD editing, that's just brilliant, super cool. That's really, really cool. I wish we could do that with our the OSD on other systems. Very, very nicely done. So, any questions about Brandon? Go ahead.
All right, so I saw with the firmware update, was that certainly you could update the firmware on the ArduPilot. Can you update the BlueOS version as well?
Yeah, that was the.
Go back to both.
So this was the BlueOS version.
Yeah, this updates BlueOS. So this changing the Docker, and then go back, and then within there we have firmware flashing tool. That's this one.
So you do both.
Yeah. Is that supposed to be a GIF, right? Yeah. So it fetches the manifest from firmware servers, checks compatibility, and then downloads the firmware. Yes. It's embedded into it. If it detects a navigator, it fires, just starts ArduPilot. If it doesn't, if it detects a pixel, then it doesn't. I mean, includes, yes.
Yeah, so.
Yes.
Is it an extension?
No, it's built in.
So that's one of the internal services that's built into part of the core image.
Good.
I was thinking the selection of sort of simple versions that you go with, sort of static, but it actually looks like actually seeing a demo of that right now as you're selecting firmware versions. Is it tied in, does it always grab the latest civil release or a stable release, or you select that when you're doing the civil?
I don't remember.
Yeah, I can't remember what the deal is there.
Yeah, I'm sorry, I don't remember exactly how that's done.
No worries.
We actually still have an issue with Zero that we have to get the default parameters sorted out properly.
Right
so
now. I'm wondering, so the civil we do with Mission Planner comes from one's built in Sigwin on our CI system.
Yes.
We don't actually build and distribute civil binaries for other platforms. So that's why I was wondering how you actually go and build it on the Navigator, or do you pre-build? Yep. Oh, we do.
Okay, then that's probably where it comes from.
Yeah.
Because I don't remember rebuilding it ourselves. That would be weird. So it's probably coming from somewhere.
Okay.
Yeah.
How easy or difficult is it to build a custom application on this? Say, for example, I want to build a diagnostics application for a log which exists on the vehicle.
So the extension architecture is made to be sort of quite simple. As William was explaining, there's not that much that's involved in terms of the files. Like the HTML and JSON here are only relevant if you want a web-based interface. The code can be basically anything you can run on a Raspberry Pi. And our APIs for internal services are sort of testable via the interfaces provided. And then the Docker file metadata requirements are documented.
Yeah, I guess the answer is it's very easy to run some Python code to analyze logs and show the output on a page that's a link on the sidebar.
Yeah.
I'm not sure if that's the underlying question.
Yeah.
Okay.
It's very easy.
Yeah.
On the
What?
Are you asking, can we do waypoints in our GCS?
Yeah, under the water.
Under the water. So if you have a positioning system, you can, but our GCS currently has been like doesn't yet have mapping or waypoints in it.
It's the next step because of this guy. So we have to start supporting the positioning. There are both underwater GPSs, which work as, let's say, sound satellites. So you have like multiple transceivers and then a receiver on the vehicle. Yeah, they're like beacons, I guess.
Yeah. And then DVL, as we were talking about.
And the DVL is my favorite because when it's locked, it's very precise, and it's just beautiful seeing like your ROV just ignoring the water current and locked in place. Any more questions? Suggestions?
All right, so thank you very much.
Thank you.
So that today's presentation. Now, the original plan for the conference was that it would just be a free-for-all, get your own dinner, whatever you like for Friday evening. But we decided that we would try and make a group booking. And so we do have a group booking for dinner right down by the lake. I'll just pop it up here for the information so you can decide whether you're going to go along. And let me pop that up. Now, is that going to come up? All right, great. And I should be able to turn on my audio here. So for other people,
there you go. All right. So it's down at this spot here. It's about a 19-minute walk from the hotel, or you can, of course, drive. And it's a rather nice spot. Let me just find the Jetty Canberra. The Jetty Canberra. So it's a spot right on the edge of the lake like that. And it's burger type meals, sort of chicken burgers, that type of thing. There are vegetarian options. And I put the menu into the conference chat on Discord in case you want to look up the menu. So we've got a booking there for up to 60 people, so we could have everyone at the conference at 6:30. And option is to walk down together as a group or to drive down. It could be a bit chilly. There are some indoor versus outdoor under the awning, so there'll be some warmer seats than others. And I've got a few extra jumpers in my car in case people didn't bring an appropriate jacket. So how many people think we're going to be joining us down by the jetty this evening? Okay, looks like most people. Fantastic. All right, so that starts so the booking is for 6:30. And so feel free to get there a bit earlier. Otherwise, just feel free to chat among yourselves or go for a bit of a wander. And look forward to seeing you all down at the jetty, maybe 6:20 or so, and for dinner. Thank you very much for a great day.